I think it's the concentration of expertise in C++ specifically. I mean, it's all in the name. It's been really great to just like hang out with these experts and just like pick their brains and, you know, absorb their knowledge.
No, that would be a linker error, Christian. Yeah, exactly. You know, we talked about that, right? Yeah, go talk to Bartosz. He can help you. He's pretty good at all this. Okay, see you next week. Hi. That was Christian. And Christian, he is one of the extremely talented hardware engineers that work in my company. He comes from university, and he knows everything, like everything about impedance matching and hardware loops, ground routing, analog circuits. But what Christian does not know, and what nobody taught him at university, is that being a hardware engineer today is like 20% software development. That sucks for Christian. So when Christian designs a new PCB, we all pick a chip together, one we think will do the job, and then he designs a PCB, builds a prototype, and then he's gonna make sure that it all works. So he starts typing, and he downloads the IDE from the chip provider. And when he's done typing, he presses the big green button, and then nothing happens. It doesn't work. And Christian has absolutely no idea why. So Christian calls me, or some of my colleagues, and we go to him, and we see his problem, and we explain, oh, that's a linker error. It means you didn't include your file there or that. And then everything works. And if you're like Christian, that you are going to program, and you don't know exactly what goes on, then maybe you're in the right place. Because we're going to figure out what's beyond the big green button. My name is Morten, and I'm a senior firmware engineer at Welltech in Denmark, where we do oil well robotics. And today I'm going to take you through the entire build process, from your typing, through preprocessing, compilation, linking, flashing, and then questions at the end. But first, a word from my employer. We do robots that operate in oil wells. We are a service company, and when something goes wrong in an oil well, well, who are you going to call? Welltech. Those are some pretty unique constraints. The oil wells are thin, pretty thin, and it gets warm down there, and it's high pressure, and the acidity is not for fun. And since we also operate in gas wells, please no sparks, which rules out steel, because steel sparks. We develop everything in-house, because you can't buy stuff that is so small it goes down a 5-centimeter hole. On the other hand, we have infinite length, so our tool robots can be up to 30 meters long. We do a mix of embedded Linux, bare metal, and lots of communication protocols. And our operators, they have a desktop laptop PC with a .NET application. So what is the build process? The build process starts with you typing code. That's up here. That's not really a part of the build process, but it is necessary before we can continue to the first step, which is preprocessing. Preprocessing takes your code and processes it, prepares it for compilation, and the next step is compiling. So you type your code, store it in C++ files, you feed it to the compiler that performs a preprocessing step, which in turn creates an intermediate file, a .i file. The .i file is not stored on disk, so in reality, compilation includes both preprocessing and compilation. The output of the compilation are object files. We got them down here in the linking stage. Object files contains machine code, primarily machine code for your processor to execute. It does contain other stuff that is useful in debugging sessions, but for this talk, it contains machine code. So the linker takes the machine code and the libraries that you use, and it reads a linker script, and then it links them together into one final hex file, which is the one you will be flashing onto your device. And if you have a happy green button, your device works as expected. If you have a grumpy green button, nothing works, and your we'll need to figure out why. At this point, I feel it's important to point out that this build process is actually very similar to any other build process of C++. If you develop for cluster, for laptop, for operating systems, it is the same. The main difference is the linker script and the hex file. If you develop for an operating system, you don't need a linker script because what is in the linker script is defined by the API of the operating system and is as such already known by the compiler and the linker. So that is the build process. Once the build process is over, you can use a tool of your choice, or rather your chip manufacturer's choice, to flash that hex file onto the device. So we're going to look briefly at how include statements are resolved, how macros are resolved, and then, just for your knowledge, comments are removed. So any comment you type are removed during the pre-processing stage. We're not going to talk about conditional compiling. You will figure that out soon enough, and the errors are the same as we will see from the macro resolving. On the left, we have a tiny C++ file that does nothing but include a class file and instantiate a single instance of that class. Now, I told you that the intermediate files are not stored. Well, typically they are not stored. You are able to instruct your compiler that you want all the intermediate files saved along with your final files. But we can also, if you use GCC, we can tell GCC, please compile this CPP file, but stop after the pre-processing and output the intermediate code. That's awesome, because it will give us a way of introspecting the pre-processed code, and as such we can see what goes on. If stuff doesn't work as expected, we can get a hint by looking at that. So on the right-hand side, we have the intermediate file of our C++ file. At first, we have a bunch of lines with hash marks at the beginning. We'll ignore them for now, and just conclude that class.h, the include statement up here, has been replaced by the content of the class.h file. Almost. It has almost been replaced. You'll see there are something with new lines that have been resolved. I'm not sure why that happens here, actually. I think it's because the preprocessor works on tokens. It doesn't understand what it's doing. It's just tokenizing your code into chunks, into words separated by white space. And apparently it felt like removing a white line. So what we can see is that we here have the preprocessed code ready to be compiled. And just for the lull of it, let's take a look at the line starting with a hashtag. The hashtag lines are information from the preprocessor to the compiler, and that's pretty useful information. Now, let's assume that we had forgotten a closing semicolon in my class, in the class.h. We would also lack the semicolon here, and that would be a compilation error. We'll talk about that later. And where would that compilation error come from? Well, that would come from main.i. So if you get an error message with a main.i, you will go look for main.i and you will not find it. So primarily, these lines with hashtags are information to the compiler about what original file are you actually compiling now, so that you will be able to output a proper output error message to the user. So this way you can introspect your preprocessed intermediate files. The thing with intermediate files is that they can grow pretty huge, and if you're not careful or do a thorough search, you can end up with a lot of code. Now consider this main file again. We added included vector because we want lots of mod classes, and then we needed a size of them, so we include standard def. And on the bottom, we can see that those 6 lines of C++ code results in almost 20,000 lines of intermediate code. So there's quite some code to dig through. So if you have a problem and you're investigating the preprocessor, put in some words you can look for, because there's a lot of code to look through. So having included, the preprocessor does the macro expansion. And macros are like sort of dumb functions, and you should really not use them. But you will meet them, because they have been used extensively throughout the lifetime of CPP, and you will meet them. So let me talk a bit about the errors you can get from a macro expansion. We have on the top side, we have a file 5 lines of code, and where we define a macro that calculates the power to 2, should be power to 2, of whatever you put in the parentheses. So looking at the top main, you see that 4 equals the power of 2 to 2, and 9 equals the power of 2 to 2 plus 1. And that sounds fine and dandy. We run it through the preprocessor, and for your convenience, we leave out the information from the preprocessor to the compiler. And what we end with is this down here. It says 4 equals 2 times 2, and 9 equals 2 plus 1 times 2 plus 2 plus 1. Excellent! We have a successful macro expansion. Except that it doesn't do what we want it to do. Because the macro and the preprocessor does not know about code. It only knows about words or tokens separated by white spaces or semicolons. So what it does is that it simply takes the power of 2, that's the macro up here. The preprocessor says, okay, I'm going to take A, and A, that is 2 plus 1, and then we're going to print 2 plus 1 times 2 plus 1, yielding this, definitely not 9. So this is the thing with the preprocessor. It's super dumb. It does exactly what you ask it to, and not what you want it to. So the solution to this is to use ample of parentheses. Parentheses, parentheses, parentheses. It's not going to incur any cost runtime. Quite the contrary, it's going to make your code work and work as you intended at runtime. So when you construct your macros, be sure to parenthesize everything. I mean, everything. More parentheses are better when you're making macro expansions, because it will now be resolved to the first parenthesis, and then the second parenthesis open, 2 plus 1, parenthesis close, times, parenthesis open, 2 plus 1, parenthesis close, and that will yield 9. So if you are having some weird problems at runtime, say this was not 9, but it was, for example, the angle a cutter should rotate in order to cut a steel pipe down the hole, it wouldn't rotate enough, and we wouldn't know why, because the code built, there were no complaints. We typed in 2 plus 1, that should yield 9, it does not. So if you have some kind of weird behavior and you're pretty sure about your logic, make sure that you do not use macros, and if you do, make sure that you litter them with parentheses. It is super important. And then I'm going to take a bit of water while you behold the 4/1/18 grinder that we can send down and grind rocks and broken valves, because there's a valves downhole. So the next thing that can go wrong, the thing that can go wrong is the include statements. And this is trivial, but the takeaway here is, how do we know that this is a preprocessor error? Because this is about identifying what stage does your bugs originate in, because that will help you fixing them. So again, we have a tiny, tiny main up here that includes IO stream and then outputs hello world. We compile this, and we don't stop at the preprocessor. But we get an error saying invalid preprocessing. Boop, that's a hint. This is the preprocessor state. We haven't even started looking at your code yet. It's not your for loop, it's not your logic, it's not your mismatch of types. It's simply the preprocessor. It cannot process the code. And we even get more hint. Did you mean include? And yes, that is, of course, what I meant. The word preprocessor, we haven't started looking at your code yet. We try fix the include, build again, and we see include IO stream, no such file or directory. File or directory, those are also hints. This is the preprocessor. The compiler does not care about files or directories. The linker will eventually, but it will not complain like that. So if you get the error message, no such file or directory, this is a preprocessor error, and you should not be concerned with whether your types are correct or not, because you have to look at the preprocessor. Macro redefinitions is another thing that's super annoying, and that is especially something you will see in old code base, because you have a weird include hierarchy, and they may be duplicated. So we have some code here that would like to say hello Bjarne, hello Morten, because Morten, he's super awesome, and we want to say hi to him. And it works, and then we figure out later that maybe Morten is not that awesome, we would much rather greet Bjarne. So we put in a defined name, Bjarne. What happens here is that we're redefining, and we get that error. Warning, redefine. Now, redefine could be a compiler error, but since it shows us the define statement, we know that this is a preprocessor. The solution to this is, of course, to remove one of the define statements, because you're not allowed to redefine macros with the same name to a new value. It would be okay to have 400 lines of define name Bjarne. It would be silly, but it would be perfectly legal. So we get the hint of the define. This is the preprocessor. And we are so kind as to be told where was it first defined, so we can go fix that. So to sum up the preprocessing, some of the messages you see are no such file or directory. The preprocessor cares about files or directories. Check your include path. Check that you have your include names correct. That's the way to fix that. Unknown preprocessing directive. Well, you have a typo somewhere in your hash something line. Macro redefined. You have to watch for repeated includes. And that could be several files that include the one file that includes two files that each in turn includes the same file. Could be that error. It could also mean that you simply include the same file several times in the same source file. And that would result in errors like that. So this is a summary of some of the things you will see in the preprocessor. But look for file or directory in the error messages. And we're going to have a small side quest. We have 100 one-page side quest to choose from. So which should we take? Any, sir?
47.
7?
47.
47. Excellent choice, sir. 47 happens to be about error messages. What a coincidence. You see, at the top, we have the awesome Clang Dragon. This is the logo and the mascot for the Clang toolchain. On the bottom, we have the stylish swoosh ribbon from the Microsoft Visual Studio compiler. And in the middle, we have the derpy GNU somehow emerging from an egg, which is the GCC compiler. And I have no idea, but that's how it is. Now, the thing about this is that these three compiler messages are messages from the same error. Clang says fatal error, class.h, file not found, and then it shows us where it went wrong. GCC says fatal error, classes.h, no such file or directory. Very similar. Microsoft Visual Studio says fatal error, weird number, cannot open include file, classes.h, no such file or directory. And then it says it is in the source at line 1. And then it comes a 2. All three messages are equally valuable. They're just different. So if you're getting a compiler from a compiler vendor that has decided that that the errors should look in a slightly different way, it will not look like what you're seeing today. And that is why we focus on keywords and patterns to identify the stage where the build process went wrong. They all talk about something not being found. No such file or directory. No such file or directory. File not found. These are preprocessing errors because the preprocessor is basically the only one that concerns himself with missing files or directories. For this talk, we will be looking exclusively at error messages from GCC. And the reason we do that is because GCC is being used in a lot of compilers for a lot of microprocessors. One thing, so all these big vendors at the bottom, they have processors that rely on the GCC processor. If you are going to work on STM32R Stellar series with a Cortex-R processor inside, you should look for the Dragon errors because that toolchain is based on Clang. But we will be looking at GCC errors in this talk. And now we're done preprocessing. We're going to proceed to compiling. Our input file has now been transformed from a C++ file to an intermediate file, and we're ready to compile it and actually get some machine instructions out of it down here. Compilation is the act of turning your code into machine code. And apart from generating machine code, the two most important things that the compiler does is to check your syntax and it checks your semantics. Once that is correct, you can generate machine code. And this is probably where you will see most of your errors. And now you may think, syntax and semantics, what's what? And that is luckily 100% transferable to normal spoken languages. We do that every day. The cat sleeps. It's a grammatically correct sentence. We have a subject and a verb. That's fine. It passes the syntax and does also make sense because cats can sleep. The cat reads a book. It's completely correct grammatically. We have a subject that performs a verb on a, I don't know what that is, thing. That's valid grammatically. But cats, most cats, do not read books, so the semantics is off. It is not possible. Even though we constructed a correct sentence, cats do not read books, so it's semantically off. If anything, they sleep on the book you're trying to read. So, let's take a look at these 3 lines. Now we're compiling. Int A equals 17, int B equals 13, int A equals A plus divided times B. That is not going to work, because this is grammatically incorrect. You cannot construct a sentence that way, and the compiler says so. It says so, says invalid type of unary star have int. Means that it has an int here, and it tries to time that, to multiply that with something. But that something is not something you can multiply by. And that's what it says here. It says you're basically doing things wrong. Oopsie. No, that's right. If we take another example, the example here is we want to add a bucket of paint to a horse. We instantiate a green bucket of paint, and we instantiate a horse named Hidalgo, and then we say we want to add them together and store them in an integer. That does not work either, of course. And that is exactly what the compiler tells us. No match for operator plus, so you can't add, is what it means. Operand types are, which means you're trying to add, a bucket of paint and a horse. And then the compiler is so kind to show us exactly where it goes wrong. As a matter of fact, you can add horses and bucket of paints in C++, but we're not going to do that today. So the takeaway here is, you're doing something that is grammatically correct here, but there's no match for the actual operators. This is a remarkable different error from here. We haven't even started looking at the operators and their values. But here, the grammar is right. You can declare a variable and assign it to the sum of something, just not this something. In these cases, the fix is, of course, to either change your code, so you don't add buckets of horses and paints, and store them in integers, do something else, or you have to go ahead and make sure that there is an operator plus, so you can add buckets of paints and horses. But, as I said, that is not today. But error, no match for operator. This is a compilation error. And you can fix it by fixing the code that you have been typing, because you typed it wrong. Again, we have a small example similar to the previous one. We have an int A 17, and int C we assign to the sum of A and B. And then that is again grammatically correct. You can add 2 things and store it into something else. But B was not declared in this scope. Scope, that's another keyword. Scope happens in the compiler. So if you see something is wrong in this scope, you know it's a compilation error. You typed code that is not semantically correct because there is no B in this scope. And just to be completely sure, scopes are all chunks of code that are within curly brackets. There may be others, but at least this is a 2-line scope. So to fix this, you will either have to create a B or make sure that B is defined in a parent scope, or you have to redo your logic. But scope, it's a keyword. It's the compiler that's unhappy. And that is the Welltec 3/1/18 tractor, which is the thing that drags our tools and robots when we're in horizontal oil wells, because at that point, gravity is not really super helpful. Definitions and declarations. Those are important things when you're talking about compilation. So we will briefly discuss them. Definition is also going to be important later on in the linker stage, but I think this is a good time to mention them. A declaration is a promise from you to the compiler that in the future, somebody will write code that make add numbers work. So that's just the signature of a function or the signature of a type and a semicolon. It doesn't do anything except you say, dear compiler, this function will be available when you need it in the future. I promise, use it, allow me to use it. And you can do so. Later on, you will define that function, typical in a CPP file. So the definition is where you type the code that fulfills the promise you made in the declaration. And this is you saying to the compiler, this is how add numbers is supposed to work. Please generate code for that. And then in the future, somebody may or may not use it, but please generate it. You do not need to declare your functions before you use them, as long as your function definitions are in the same translation unit as you're compiling and before your usage. Then you can actually skip that step. But quite often you will find header files that includes the declaration. So, an overview of the different kind of errors you can get during the compilation stage. Is semicolon expected? Expect a semicolon before curly bracket token. That means you forgot to add a semicolon. A token, this is another keyword. The C++ compiler concerns itself with scopes, expressions, statements, and tokens. So this is a compilation error. And then we have the next one, X was not declared in the scope, and that comes from this, because that's similar to what we had before with the B, that it doesn't exist, neither in this or in any parent scopes. So you can't see out it. The fix to that is, of course, to make sure that that X is defined, and then or not see out it. Here we have defined, not declared, defined, because we have the body implementation too. It's a short body implementation, but it's there. So we define this function called foo that takes an int, and then we call foo with 2 integers. No matching function call for foo int. That's because you are trying to use a function that has a different signature than what you are doing. And that's of course not going to work. Not in this example. So this is something you typed, you mistyped something else. You can fix it by either adding another parameter to foo or make another way of calling foo. But no matching function call. That's a compilation error. And it gets more silly. We are trying to create a horse and pass it to foo. And then we are told that we cannot convert a horse to an int. This is a type error. We cannot convert between 2 types. So this is compilation error because the compiler concerns itself with types and statements. In C++, you can convert a horse to an int, but we're not going to do that today. Assignment of read-only variable, it says the compiler. And now that's silly. But basically it means, you are trying to store a value in something that you cannot store a value in. And that happens because in this example, you declared x for a const, meaning you cannot change it or modify it later on. So basically here it should say you cannot assign to a const variable. That would be a more fitting error, but this is the one we have. The solution to that is, of course, to either make x non-const or find a way to store your 5 in a way that doesn't violate the constness. And here's a tip. You may see a lot of const. So you have a const int, const pointer, x function const. And it can be a bit confusing as to what of all these things that are actually const. But a rule of thumb is if you read it backwards, then you will see what the const applies to. Except for the first one. The first const applies to the right. But if you have a signature with lots of const, read it backwards. And then const comes before the thing that is const. Cannot bind non-const L value reference to an R value. Wow, that's obvious. We all know what to do now. Of course we don't. What we have here is a function defined and declared as foo taking a reference to an integer. The ampersand means that now this int is a reference. And again, we read it from right to left. We can see it's a reference to an int. And then later on, we call foo with the value of 5. A reference to a variable means that this variable that we're taking a reference to shall be available for storage somewhere else. So that foo could, for example, update it. Foo could, store the double value of x into x, if that's suitable for your logic. But that's not what we do. We call foo with a value, not a variable. And you can't store a new value into 5. It doesn't make sense. And that's what it says here. It says you cannot use a fixed value as a reference to a value. That's basically what this one says. A bit confusing, but that's what it says. So the solution here is, of course, to make either foo take another reference but a copy of an x, or find some way else to get 5 into your function. Declare a variable first, assign it to 5, and put that variable in your function called foo. L value and R values, those are compiler words. There are hints that this is a compilation error. And we are just going to add more horses and paint here for the fun of it. Invalid operands of type int and string to binary operator plus. You cannot add a string to an int, this one says. You heard this before in C++. You can add an integer to a string, but we're not going to do it today. It requires some hoops to be jumped. And this is because we create a variable x equals 5, and then we make a string say containing hello, and then we're going to add them together. The solution here would be to either convert x to a string before you add them together, you can do that, or just not add them, or maybe use some other means of getting the meaning. So those are all compilation errors, and they are tokens, they are L values, they are R values, conversion errors, assignment errors, L values and R values again, binary operators. These are compilation errors. It's code you typed. Everything is fine so far. All your macros have expanded, all your include files have been found and properly included, but you typed something wrong, or your colleague did, and now you have to fix it somehow. You can do that by retyping the code. Yet sometimes it's not as obvious where things go wrong. Now I'm going to take a sip of water, and I would like you to read the main function, the C++ to the right, compare it to the error message. Read the C++ on the left and compare it to the error message on the right, and see if you can figure out what went wrong. And then I'll get back once I've had my water. Anybody other than Bartosz that realizes it? Yes, sir? The x is lowercase, he says, and not uppercase. And that is correct, and that's a typo from my side. That is not the error. Thank you, I wasn't aware of that. Sorry, that's a typo. It is not that. Extra semicolon, exactly, sir. The thing is, as the error message as politely points out, else without a previous if. No. There's an else, there's an if. But the implicit part of this error message is that in C++, you need to have an if, a condition, a single statement, and then an else. And that is not what we have here. Because when we run this through the preprocessor, the print x macro, it's now correct, by the way, thank you, sir, replaces the print macro with standard out hello, and then end line and semicolon, semicolon. Because the preprocessor does not care about code. It only concerns itself with tokens, text, and white spaces. And as I said before, you can separate statements with semicolons. So right here, what we have is an if statement, and the condition, and then we have one statement that prints, and then we have an empty statement. And now suddenly we have if, condition, statement, statement, else, when the standard clearly specifies you should have if, condition, statement, else. So what's the way to fix this? One way could be, of course, to add curly brackets, because one set of curly brackets resolves to one statement. So no matter how many statements you have in your curly bracket, that is still a single statement from the compiler point of view. Another, and in my personal experience, much better way, is that you agree in your team on, do you put the semicolons after your macro invocation, or do you apply it in your macro? It's just a convention you have to agree on. On that note, I also do prefer curly brackets after all conditional statements, but that's a very personal taste. So, where does this error come from? Is it a preprocessor error? Is it a compilation error? Yeah, well, surely it's a compilation error, but it originates from a preprocessing directive that you had malformed. So it's not easy, and it's not always that straightforward to figure out what's wrong, which is another good reason to try to limit your use of macros. Unfortunately, they're there, and a lot of us use old code base with macros. And then we have this abomination of an error message. If anybody can actually read this, then I think you're awesome. But let's take a look at the code first. The code is it's code for a barn. It models a stable. So we have a class stable. It's a template class, and you can put anything of type T into this stable, it says. So we have an animal of type T. We don't know what T is yet. It can be anything. It can be a horse, a pig, a cow, chicken. And when we want to go listen to the stable asks the animal to make a sound. Cool. Down here, we say now we want a stable of integers. Well, that doesn't make sense, but we don't know yet. So we call it an integer stable. Now we want to hear what integers sound like. So the stable asks the integer to make a sound, and of course an integer cannot make a sound. Well, in C++, yada, yada, yada. So what happens when the compiler discovers a statement where somebody wants an animal of type integer to make a sound? Well, then it says this. And what it says is that request from member function make sound in blah, 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 and this is also a bug. Sorry, I have to figure out what's wrong. Here we go. I don't know what happened. We're back. So I'm not going to use this pointing thing anymore. I'm going to use this pointing thing. I'm not going to use point anything. So what it says is that it's looking for a member function, make sound in animal, which is of non-class, line 4, type T, type int, and so on and so on. But the really important thing is in line 1, 2, 3, 4, 5, 6, at the right-hand side, where we have square brackets with T equals int. This means it's a template error. You have made a template where you expect a function to be available in a type that does not provide it. Again, your code, you can fix it. You could, for example, stop making stables of integers, or you could listen to do something else. But template errors, these originate in the compiler. This is a compilation error. And this is a short one. I mean, they can literally be pages upon pages upon pages of error messages. It can be very confusing. So if you get an error this long or longer, it's a compilation error. So compilation errors, just to sum up. It's about expressions, statements, scopes, types, and templates. It's all code that you typed. So it's errors you can fix by typing your code differently. This is, of course, a truth with modifications. Sometimes you rely on code other people typed. Sometimes you rely on a library that you bought or got, and of course they make compilation errors. But it's something you can fix in code, which is a nice thing to do. And now we're going to linking. At this stage, every single of our C++ files have been preprocessed into intermediate files and in turn converted into object files. So these are now going to be linked. They're going to be linked with the libraries that you're using according to the linker script. So the linker takes all your object files, it takes all your libraries, it squashes them together according to the linker script, and creates a single hex file that you can flash. And it could look something like this. Add numbers and other functions, the main function, they're stuffed in one end of the hex file. Then you have more functions and the libraries that comes from the compiler, for example, and from the chip vendor. And if you bought one, I mean, I bought a TLS library once because it was an awesome TLS library and we needed that, and you shouldn't do encryption yourself at all. And then it squashes, the linker squashes all your code and data into the hex file according to this scheme. Exactly where the text segment goes, where the const segment goes, BSS, data, that depends on your linker script. And your linker script is tailored towards your chip and the flash and or RAM that it has been paired up with. And what are these? I'm feeling adventurous today, we're going to use this again. Then I have to turn it on, or off and on again. No, I'm not. That's too bad. Okay, the text segment is a part of your hex file. And the const section is a part of your hex file that goes into the flash. The BSS goes also into the flash, and the data may also go into your flash. At runtime, though, the text segment and the const, they reside in the flash still, but the BSS, the const, the BSS, and the data segments, they're copied into RAM before execution of your code starts at all. The text segment contains the machine instruction that the compiler created. This is your program. That is what's being executed. The const section of the hex file contains the read-only data, the ones that we marked as const. And string literals, if you type in, say, hello, to pen it out, the character sequence hello, it's also put in your const segment. It's things that you cannot change at all at runtime. The BSS section contains global variables and static variables that are either unintentionally zero initialized or initialized to zero by you. That would include a lot of the built-in types. They're not initialized to something known. So they could reside there. And then we have the data segment, and these are variables that have been initialized by you in your C++ code. For example, global constants you assign to a string that could be the IP address of the server for which you will be looking for firmware updates. And then in the RAM, we have the heap and the stack. That's the remaining parts. The heap is where your dynamically allocated memory resides runtime, and that grows downwards. Your stack is where your function calls and your scope-dependent variables are stored at runtime, and that grows upwards. Now, should they clash, then you're in trouble. And on a lot of embedded systems, you're not actually allowed to use dynamic allocation, meaning that the heap will not be used at all. The MISRA standard specifies that if you use new, you should better have a darn good reason, and you need to document it, because it's dangerous. It's dangerous because you can run out of heap, and it's dangerous because if you leak, then you run out of memory. And one of the chips that we use in my company has a mind-blowing 512 bytes of RAM, meaning there's not a lot of leak we need to have happening before we can't execute our program anymore. So be very careful with new if you are an operating system-less project. This is a sample linking script. Under most circumstances, you will not need to modify that. Under most circumstances, it will come from your IDE or from your chip vendor. And I'm not going to go into details with that. Basically, it tells the linker where the RAM is, what goes to flash, and what goes to flash, and then later into RAM, the data, for example, and that the BSS should go to RAM. You shouldn't mess with that. What's more interesting, I think, is what can go wrong, and what are the error messages we can get during the linking stage. The first one is a tough one. Region flash overflowed by X bytes. That means your program is too large. your program will not fit into your current hardware. So what can we do? I mean, we can buy a larger chip. That's one thing. We can buy a larger RAM, but maybe your chip doesn't support a larger RAM chip. Maybe you hit the limit. So in that case, the only thing that's left is to cut features. Remove libraries, remove the standard library, runtime type information, out to the right. And probably you shouldn't be using a lot of the standard libraries container classes anyway, because they do dynamic allocation in many cases. But Flash Overflow, you really only have one thing to do, and that is to cut the size of your program. The next one is similar. Region BSS will not fit into region RAM. You have declared more variables than you have space in your RAM. Not much to do. The same thing you can do, buy more RAM, add on more RAM, or rewrite your program. And now we're taking the bottom one first, because that's better. Undefined reference to foo. Now, at some point, your code, you expected a function named foo that took an int and returned an int. And you had a header file that say, hey, a pinky promise it will be there later. But you know what you did? You broke your pinky promise, and now it's a sad compiler. It's a sad linker. Because there is no reference to foo. The linker cannot find any machine code that will carry out the actions that you expect foo to carry out. So what can it do? The only thing it can do is say, nah, sorry, no can do, sir. The way to fix that is to look through your code. Is foo defined anywhere? Not declared, is it defined anywhere? And if it is defined in a file, go to your IDE's project settings and check that that file is actually compiled and linked into your project. Some IDEs, by some compiler vendors, by some chip manufacturers that are not very good at making IDEs, will find the file on disk, will show it in your IDE as if it is a part of the project, will not compile and not link it, but it will appear as a part of your project in the file tree to the left, and that is annoying. So just because the file is there and it looks like it's a part of your project, it is not necessarily the case. So go check your project setting. On the other hand, we have the second bottommost line, multiple definitions of foo. That's because you were so eager to keep your promise to the compiler and the linker that you actually did it twice. This can happen if, for example, you define foo in two different files that are both linked together. It will not be detected compile time because compilation is on a per translation unit basis. So if you have the same function definition in multiple files, everything is fine until you link it, and then the linker says, wow, you kept your promise. Gee, I'm happy. But you did it so good, there are two of them. Which one should I use? There are multiple definitions of foo. So the way to fix that is, of course, to check. Look through your files, figure out, do you actually define foo in two different files? And if you do, well, remove it from the one of them. That can, of course, lead to other compilation errors because now the file from which you removed foo lacks it. So you will probably have to refactor your code to accommodate that. Or if you see that you only define foo in a single file, well, then go to your project settings and make sure that that file is only linked once, because you can, in several IDEs, fairly easily add the same file twice. It will compile great both times, no problems, but the linker will be confused. What should I use? So make sure there's only one definition of foo in your code base. And that leaves us with flashing. Flashing moves your hex file to your target device and stores it either on the external flash memory or on the chip's internal flash memory. And that is why we have a truck, because we're moving hex files now. There's not much to say about this, because it severely relies on the programming tool and the dongle that you have been, that you're forced to use, that you have to use because you're using that chip. But we'll take a look anyway on two popular tools. This is errors that comes if you flash using a tool on, let's say, a Cortex M0 device. Then and I've gotten all of these. Error, unable to connect to target. whoa, target, connect. We are out of the linking stage. We completed our build process. Everything went well. We are having something to put onto the target. No device found on SWD. SWD is the Cortex M0 protocol for flashing your hardware. So power it on or connect it. That's what we have to do here. Fail to read ID code from target via SWD. Well, either they specified a wrong chip in your IDE or you're trying to flash a wrong board. Maybe you got a previous prototype with a different chip. Make sure they matches. Flashing program failed, device is read protected. Well, there are probably some fuses you need to set or unset. Fuses can be used to prohibit further programming of your device. So it's probably write protected. Verification mismatch at address whatever to whatever. It is probably a corrupted hex file or a linker script that is not matching the device you're having. Timed out waiting for ACK response. Well, it lost connection somehow, and that is a very common case. Plug it on and plug it back in again, or hope for the better. It's hard to do much about that. And then the PIC kit, if you're using this before I mentioned the chip producer, it's used for microchip devices. Target device not found. Well, either you didn't connect it or it's not powered on. Some PIC kits from 3 and back were unable to power your board, so you had to supply external power. From PIC kit 4 and upwards, they are most likely able to supply power to your board. Again, ID device mismatch. Well, you ask the flasher to flash a device that is not being found, but the good news is something is found. Target VDD not detected, no power. Use a newer PIC kit and make sure that your device is powered on. BPP voltage out of range, it's again similar. I've gotten that a lot too. Make sure that your board is either powered with the correct power or at all. But the PIC kit errors and the Cortex errors, they are very, very device specific. And it is hard to keep generic devices here, advices here. The only real thing to pay attention to is to whether it complains about connections or power or mismatching IDs and similar to that. If you see that error in your IDE, then you have passed the build stage. Your code compiled, it linked, it became a hex file, and now there's a problem somewhere in the process of moving it. And those are the keywords you can look for. If you are flashing your device from a Mac or a Linux machine, then these errors can all originate, and you can check, and everything is powered correctly up, and everything is wired, and your device is happy, it consumes the joule it's expected to consume, and yet you get some of these errors. If that's the case, and you double check your connections, and you double check your power, check that you have the right permissions. Most of these chips, programmers show up as serial ports or some other kind of USB device. And if you are not in a group or a user that has write access to these devices, then the operating system will say, no, can't do. And many of these programming tools, they don't know the difference between sorry, you're not allowed to, and sorry, it's unconnected. So on those two operating systems, make sure that you have actually privileges to access it. Right. I did not cover Make and CMake. And that's simply because we have 6 minutes left, and I can't make it. I was too optimistic. I will, however, once we're done, go to conference room B, and I'm happy to continue there to elaborate on Make and CMake if you want me to. Apart from that, it's time for applause. Thank you.